right, here's another practice problem because practice is the key here. Trust me. So what is the pH of type question? We go down the list in the flowchart. What is the pH of? As we read our question, we've got a solution prepared by adding blah, 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 phenylamine, which is also called aniline, to blah, 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 hydrobromic acid. We have two things in our beaker, and the flowchart says if we have two things in our beaker, the first thing is we just go down the list and identify each. So phenylamine, acid, base, or salt. It's definitely not an acid because its name is not blah blah acid. It's not a salt because salts have two names to them. It will be the cation, then the anion. The question is it a base? And if you're not familiar yet, you should be getting familiar that blah blah amines are bases. If you're not sure, check your KB table, and as you scroll down it, you absolutely positively see phenylamine on the list. It has quite a complicated formula, but we don't have to worry about it. We can abbreviate it. You absolutely positively can abbreviate this base formula and the acid formula unless the question specifically asks about the formula. So it is a base. It is not a strong base. It's not on our list of strong bases. Therefore, it is a weak base. And I am going to symbolize it with the B because I don't want to have to draw the formula every time. As we get to our next species, it is hydrobromic acid. I think you can see very clearly that it is indeed an acid. Is it a strong acid or a weak acid? And hopefully by now you've figured out that to keep the list of strong acids handy, and this is indeed a strong acid. And again, it's just as easy to call it HA or by its real formula, which is HBr. Hydrobromic acid is HBr. So I have a weak base and a strong acid. And once I identify that there are two things in my beaker, one of them is an acid, the other one is a base, go back and look at your flow chart. The next question is, are they conjugates or not? And in order to be conjugates, their names and formulas have to be almost identical, and these are obviously not, and so these are not conjugates. And on my flow chart, go back and pull up that sheet with the flow chart. If I have an acid and a base that are not conjugates, what do? I run a reaction. I run a reaction. It's a forward reaction between the acid and the base. And an acid plus a base yields a salt plus water. And it is a limiting reagent reaction a la Chem 1. So I'm going to run the reaction between the acid and the base. It is hydrobromic acid plus the phenylamine, and I can write that simply as the base, the B, all right? And what I see when I run that reaction is the acid and the base. I don't actually get the water. Whenever you run a reaction with ammonia or an ammonia type base, an acid-base reaction, with ammonia or an ammonia type base, you don't get the plus water in this acid plus a base yields a salt plus water. The plus water comes when you have a base that has a hydroxide ion. Ammonia and ammonia type bases don't have a hydroxide ion. They do act as a base, and recall that a Bronsted-Lowry acid donates his H+, the base accepts the H+, so I think that you can see we get the BH plus ion, and that leaves us with the Br minus ion. These two are the salt. Oops. The BHBr. If this was ammonia instead of phenylamine, it would be ammonium bromide. Since it's phenylamine, it's phenylammonium bromide. I get a salt. The product of these two reacting with each other is just the salt. You can either write it as the combined ionic compound, or in this case, I've broken it apart into the ions to begin with. And so this is my limiting reagent problem that I'm going to use the numbers in the original question to decide on what's left over at the end of this forward reaction. I'm going to do it in millimoles. You can do it in moles if you want to. You can go ahead and convert to molarity, but it makes your math a whole lot harder. So my phenylamine, my base, I'm going to do him first. It's 180 times 0.52 or 93.6 millimoles. My HBr is 120 times 0.6 or 72 millimoles. These guys start off at 0. I actually don't have an equilibrium. I have a final amount. And so as I come down here, I see that my HBr is my limiting reagent. So I'm going to do minus 72 plus 72 plus 72. And again, I'm doing this in millimoles. Y'all check my math. If you find an error in the math in these videos, please give me a heads up. I'll redo them. And so at the end of this reaction, I have to ask myself again, what's in the beaker? It is what is the pH of when these are the things in my beaker. So I have some base left over. That's my phenylamine, which is my weak base. So I've got some weak base in that. And I have a salt. Now I've gone ahead and broken it into the ions as I've written this reaction, but I do have this salt. And so what do I do for a salt? I look at each ion and decide if it's acidic, basic, or neutral. And the bromide ion is neutral. That came from the HBr, which means I can ignore him. But the BH plus ion is the conjugate acid of phenylamine. It's the phenylammonium ion, which means it is a weak acid. The conjugate of a weak base is a weak acid. The conjugate of a weak acid is a weak base. So the two things I have in my container that I now have to pay attention to is phenylamine and phenylammonium ion. I have two things in my container. One is an acid, one is a base. The next question I ask myself, we're going in circles here until we get to the final answer. Are they conjugates? And they are. And they have to be. Once you've done the acid-base reaction, if you're left with two things in the container at that point, they have to be conjugates of each other. So I'm left with two things in my container. I'm left with this phenylamine. I'm left with 21.6 millimoles in, let's see, 180 plus 120 in 300 milliliters to get my concentration. Oops. All right. And I'm left with the BH plus, that is the phenylammonium ion. That's the weak acid in this pair. I am left with 72 millimoles in 300 milliliters. So this is a buffer problem. I have a conjugate acid-base pair. This is a buffer problem. It requires one ice table. You can either work it as an acid or a base. Which one you pick doesn't matter, but typically one way versus the other is easier mathematically because you have a K value for it. I'm going to choose to work it like the base. So I'm going to write the generic equation for a base in water. That gives me my BH plus OH minus. If I'm working a base problem, a weak base problem, I need to make sure a weak base problem should be producing that OH minus. I'm working it as a base, so I get the OH minus at the end. A weak base problem, there is a KB value, not a Ka value. And the KB value for phenylamine is 4.3 times 10 to the minus 10. I'm looking that up in the table. So now I have an ice table. I have the molarities up here to plug into it. So the base concentration is 0.072. I would be keeping extra sig figs, except for that's all the digits I get. The acid, the BH plus concentration is 0.24. Let me double check that. All right, let me double check the other one. Yep, that's right. And again, I would be keeping extra sig figs, except for that's all my calculator gives me. I have 0 here, minus x plus x plus x. It's starting to look familiar. And now I'm ready to plug into my equation. 4.3 times 10 to the minus 10 is equal to 0.24 plus x times x. Actually, I think I would need to move this down. That might be cut off on the handout. Divided by 0.072 minus x. I'll use the approximation method. I will approximate that this plus x and that minus x are very, very small. This almost always works on buffer problems. So my math becomes very simple. Oops, that's just it. And I will solve for x. Give me a second to calculate it in. You should be punching along with me. And I get 1.29 times 10 to the minus 10. That is a very small x. The approximation method is fine. Do recall that this is x is the OH minus concentration. And so from that, I can get the POH by taking the negative log of it. 9.889 dot dot dot, which means the pH is, how about 4.11? And so again, this is just more the same, but we're building. It's a longer problem because you have to keep iterating down until you get to the final process that allows you to calculate the pH.